Hello and welcome to our video on problems involving titrations. Today we're going to be going over some common problems involving titrations and how to solve them. I'm going to be introducing you to the topic of back titrations, and then we're going to be looking at some problems involving back titrations. So in question 1, it says that it takes 38 milliliters of 0.75 molar sodium hydroxide solution to completely neutralize 155 milliliters of sulfuric acid solution. What is the concentration of the sulfuric acid solution? So basically, when it says neutralize, I want you to imagine that we have a burette of sodium hydroxide, and in that burette, I've had to take out 38 milliliters to completely neutralize the sulfuric acid solution that's in the beaker underneath the burette, and there's about 155 milliliters of sulfuric acid in that beaker. So question 1 is an example of a fairly straightforward titration question that you're going to get. So essentially you're going to be given the concentration and volume of a reagent, in this case sodium hydroxide. You're given its concentration and its volume, and you're asked to either find the concentration or the volume of the analyte. In this case, the analyte is sulfuric acid. A key relationship that you'll need to know to do these questions is C1 times V1 equals C2 times V2. It's really important that you memorize this, but I'll show you how we get to that relationship. So N1 equals C1 times V1. And let N1 be the moles of sulfuric acid. N2, on the other hand, equals C2 times V2. Let N2 be the moles of sodium hydroxide. At the equivalent points of the titration, the moles of sulfuric acid will equal the moles of sodium hydroxide. Thus, the product of their concentration and volume will also be equal, and it will give you this relationship here. Thus, it's really important that you know this. It'll come up in a lot of questions throughout your whole chemistry studies, but especially in regards to titrations. If we plug these numbers in, we get something like this. So always never forget, write your formula first, substitute, and then answer. And one thing I want you to get into the habit of is using scientific notation. For example, if I were to write 100 milliliters, this formula and any formula in chemistry only accepts SI units. In this case, liters. You could write that as 0.1 liters, but I never took the risk. I said 100 times 10 to the power of minus 3, because a milliliter is 1,000th of a liter. I always put the 10 to the power of minus 3 so I can see what I was doing, because I just didn't play around with decimals, and that saved me a lot of marks. But if you rearrange, you should get 0.092 moles. Also, don't forget your significant figures. Now that you know the basics of how to set up a nice working solution, we'll go through another question. So in question 2, we're asked to calculate the molarity of an acetic acid solution if 34.57 milliliters of this solution are needed to neutralize 25.19 milliliters of 0.1025 molar sodium hydroxide. And as a bonus question, I want you to tell me which indicator we would use for this titration. So in effect, question 2 is quite similar to question 1. You're given the concentration and volume of a reagent, in this case sodium hydroxide, and told to find the concentration of the analyte, in this case acetic acid. The first thing I like to do is show my equation, which I've done up here with all the correct states, and then show my formula, which will usually earn you a mark, show my substitution, which is usually another mark, and then the correct answer. Note how I've used times 10 to the power of minus 3, as I've been given units and volumes in milliliters. realistically, if you use the same units on both sides, it won't matter because it's a ratio, but I don't take the risk. Whenever I see units, I always use any units I see, I convert immediately to SI units using a power of 10. And I recommend you do the same, just to avoid any confusion. But if you have a method and it's working for you, keep at it. And the bonus question, the answer to it is phenolphthalein. As this is a titration between a weak acid and a strong base, you may recall from a previous video on titrations that we use phenolphthalein as an indicator for these titrations. Now I shall introduce you to the concept of a back titration. So for any titration, whether that be a simple titration, which is what you've been exposed to so far, or a back titration, our goal is always to find the concentration of the analyte. You may ask, why would we do a back titration after understanding the method? There are a couple of circumstances in which we would actually need to do a back titration, and we're going to go through those in a couple of slides' time. But for now, I want you to focus on the method. So basically, a back titration is where we have the analyte that we want to determine the concentration of, and the first thing we do is add an excess amount of our first reagent. We're going to go through a worked example in the next slide, but I want you to just have a nice foundation of what I mean. So if I add an excess amount of a reagent, this being reagent number 1, so I'm going to say number 1, R1 plus our analyte will give me my product plus an amount of excess R1, right? Because if I add R1 in excess, enough R1 will react with A to form the product, A being the analyte. However, there will be a lot of R1 left over, and that is represented by our excess. We then take this excess and we perform a titration with it. And then we use another reagent. So in this case, reagent number 2, which might be sodium hydroxide, for example. We take it through a titration to find the exact amount of the excess reagent. So if you know this, we know how much we added. So if we know how much is in excess and we know how much we added, we know how much was used to react with the analyte right here. And we get that by just minusing those two number of moles. So for example, if I add 10 moles in excess to react with the analyte, and from the titration, I found that I have 5 moles in excess. That means 10 minus 5, 5 moles were used to react with the analyte. Then I can use molar ratios. So in this case, the ratio of my reagent to my analyte is 1:1. So if 5 moles were used to react with the analyte, there's just 5 moles of the analyte. And then depending on the volume of the whole system, I can find the concentration. This will be a lot more clear in the next slide when I take you through an example, but just bear this explanation in mind. So this is a pretty common method that we'll come across, and I'm going to use it to demonstrate back titrations. So as I said, we have calcium carbonate. This is our analyte. We then add excess HCl. So that's reagent number 1. And it gives me something like this equation here. So calcium carbonate reacts with HCl to form calcium chloride, CO2, H2O, and a bunch of unreacted HCl. I then perform a titration with this unreacted HCl with sodium hydroxide. So if you can imagine, I might have a beaker, this is a beaker. I have my rock of calcium carbonate, and I've just dumped a bunch of HCl in. I now have a beaker with all these things. So I have calcium chloride, draw an arrow here, calcium chloride, I have CO2, I have H2O, and I have a bunch of unreacted HCl. I then put a burette over it, take it through my normal titration method, and in my burette I'll have sodium hydroxide, and I'll take it to the equivalence point, and I'll find the exact amount of sodium hydroxide that was used to react with the excess HCl. As HCl and sodium hydroxide are in a 1-to-1 ratio, if I know how much sodium hydroxide I used, I know how much HCl there is, and thus I know how much unreacted HCl there is. Thus, the moles of HCl that reacted with calcium carbonate are what I originally added, so what I originally added in excess, minus the unreacted HCl. And that kind of makes sense. So if I just dump a bunch, and some of it reacts, and some of it is left over, by finding what's left over and minusing it from what I originally added, I can find what reacted. And then we use this equation again. We know that HCl and calcium carbonate are in a 2-to-1 mole ratio. So whatever I get from subtracting here, I just double it, and that's how many moles of calcium carbonate were present. And then this is an extra step they might tell you to do in some questions. Not all questions, to be honest. If I know the moles of calcium carbonate now, I can just multiply that by the molar mass, the molecular weight, my bad, to find the mass of calcium carbonate. They might ask you to do that, but they could also ask you to stop here. If you ever get confused about back titrations, try and refer back to this slide as just a brief overview on how they work and how to solve questions. Now you might be asking, why on earth would I do that? That is exceedingly complicated and there should be no need. There are actually 3 instances in which you would. So the first being the original analyte, what you're trying to find the concentration of that being, is an insoluble salt, such as calcium carbonate. Also, you could use it in titrations between weak acids and weak bases, or whenever the reaction occurs very slowly. So any of those 3. But for the purpose of your senior chemistry studies, it'll probably be the first one here. So any insoluble salt, you'll do a back titration on. So question 3 is an example of a back titration question that you're going to get. So a water sample was analyzed to determine the chloride ion content. 100 milliliters of this water was added to 24 milliliters of 0.25 molar silver nitrate. The mixture was filtered and the filtrate was titrated against 0.05 molar potassium thiocyanate according to the following reaction. So this is what happens with the excess silver from the silver nitrate, the thiocyanate anion, and that gives you silver thiocyanate. The titration was repeated 3 times and the average titer was 28.55 milliliters. Calculate the concentration of chloride ions in the water in moles per liter. Okay, so when you see this question, it's a lot of information to take in, and the first thing you should be doing, what I like to do, is visualize what's happening. So I'm picturing a water, big river of water, and they've just scooped up a beaker of water with about 100 milliliters of water in that beaker. You then add silver nitrate. You're actually looking at the chloride ion content in the water, my bad. Should have clarified that. And thus you add 24 milliliters of this 0.25 molar silver nitrate in excess. So you've added too much to find the exact chloride ion content. Thus, this mixture was then filtered and the filtrate was titrated against 0.05 molar potassium thiocyanate. So silver nitrate and chloride will give you insoluble silver chloride. So they've got this beaker of chloride containing water. They've added the silver nitrate to it, and silver chloride has dissolved out. They've then filtered the that mixture through, and they've got a liquid. In that liquid is all the excess silver nitrate that's present, if that makes sense. They then titrate this excess silver nitrate with 0.05 molar potassium thiocyanate. And that is the reaction that's happening. The nitrate is pretty redundant because it's just a substitution reaction. We can write it. It's not wrong to put a NO3 at the end of this silver. But yeah. The titration, so we repeated it 3 times for validity, and the average titer. So titer, meaning the amount of this needed, was exactly 28.55 milliliters. And now we need to find the chloride ion concentration. So with all these titration questions, the first thing I want you to do is remember to start at the bottom. So your goal is to find the analytes, so in this case, the concentration of the chloride anions, but you have to find a bunch of other things before you can do that. So you start with the bottom, and usually in back titrations, that's that proper titration that they're conducting. I know I've said the word titration twice, but in this case, I meant the titration that's happening between the silver nitrate and the thiocyanate, so the SCN minus. So in our little thought experiment type thing, so we're going to pick up where, so we have the beaker of water, we've added the silver nitrate, we have this insoluble silver chloride that we've filtered out, and we have this beaker with excess silver nitrate, and we're going to do a titration with potassium thiocyanate, and that is where we are. So I want you. So the first thing we need to do is find the moles of potassium thiocyanate that are required to bring the silver nitrate to its equivalence point. And we're actually given that, so we can do that with the formula N equals CV. So first thing, write my formula, and then substitute. So it's 0.05 molar, and it took 3 attempts and the final titer was 28.55 milliliters. And when I do that, I get 0.0014275 moles. I hate rounding in the middle or to any significant figures. I just write a huge number and then significant figures at the end, because look, it shouldn't really matter, but sometimes if you round too much, it can upset your answer. So I just round at the end. As the molar ratio of thiocyanate and silver is 1:1, thus the unreacted amount of silver is 0.0014275 moles. And when I say unreacted, just recall that we added excess silver nitrate to that beaker of water. Some of that silver nitrate reacted with the chloride and formed silver chloride, and some was still left in the beaker. We performed this titration to find how much is unreacted, and that ended up being 0.0014275 moles. Now, as I said, we're going to ascend. So we start at the bottom, now we're going to ascend. Originally, this is the reaction that's happening, as I said. So silver nitrate is reacting with the chloride in the water to give you silver chloride, and the nitrate anion. So this is an example of a displacement reaction. And this is an insoluble salt. So this is when I've just got the beaker of water and I've just put excess silver nitrate. So this being silver nitrate into that beaker. So this is the step where we're at. The excess that I mentioned was 24 milliliters of 0.025 molar. Again, N equals CV. This is my equation. Substitute, and I get 0.006 moles. Very handy. So that is the amount of excess, or the original amount of silver nitrate that I dumped into that beaker of water. From the last slide, I know how much silver nitrate was unreacted or left unreacted after some had reacted with the chloride. Thus, the amount that reacted with the chloride is that original amount that I added in excess, so that being 0.06 moles, minus the amount that remained unreacted that I found using the titration. And that was from the previous slide, 0.0014275 moles. Thus, if I subtract both these figures from each other, I get 0.004572725 moles, which is the amount of silver nitrate. So silver nitrate that reacted with chloride to give me this here. So exactly 0.0045725 moles were required to react with the amount of chloride present in solution. Now, if I've got the number of moles of chloride to find the concentration, C equals N over V. This is my equation. I substitute and I get my answer. Always remember correct significant figures. And the answer you should have got is 0.046 molar if you're following along. So we're going to step it up with question 4. So this is an example of a multi-level back titration problem. So there's a lot of parts to this. It's not too much more difficult than question 3, but there are a couple of extra steps. With all of these back titration problems, there's fundamentally 2 ways you can approach it. You can either just visualize what's happening and just think systematically, or if you find that you can't visualize it at all, just remembering a step-by-step process to just doing these questions. So that means working at the bottom, looking at the titration, and then slowly working your way up to find the analyte. So in question 4, we're asked, eggshells contain calcium carbonate. Fantastic. The following 2-step procedure was used to determine the percentage by mass of calcium carbonate in a 1.21 gram eggshell. The 1.21 gram eggshell was crushed and added to 100 milliliters of 0.3 molar HCl. Excess HCl remained after the reaction was complete. So that's a reaction. So calcium carbonate reacts with HCl to give you calcium chloride, water, and carbon dioxide. Fantastic. 20 milliliter samples of the excess HCl. So after it's reacted with the calcium chloride, whatever's left, we take 20 milliliter samples of it. It was then titrated with 0.1 molar sodium carbonate solution. The equation for that titration is this here. In one of the titrations, it took 9.23 milliliters of sodium carbonate to neutralize the HCl. And that was obviously the 20 milliliter sample that we took in this step. And we're asked to calculate the percentage mass of calcium carbonate in the eggshell. So in the 1.21 gram eggshell, how much of that is calcium carbonate? It's essentially what they're asking. So if you can imagine, again, we have a beaker, we have this eggshell, we grind this eggshell up, we put the powder in the beaker. We then dump a bunch of HCl. So when I say dump a bunch, I mean exactly 100 milliliters of 0.3 molar HCl. That HCl reacts with the calcium carbonate in the fine powdered eggshell to give you calcium chloride, water, and carbon dioxide. Of significance, there is also a bunch of unreacted HCl. We then pipette 20 milliliter samples of this liquid that's left. So in the beaker, we have the powder, we have the HCl that we add in excess, and that dissolves and leaves us just a solution. We take 20 milliliter samples of this solution, with the solution containing our unreacted HCl. We then titrate it with 0.1 molars sodium carbonate. It takes 9.23 milliliters of sodium carbonate to neutralize the unreacted HCl in this 20 milliliter sample. Hopefully that's a little bit more clear now. And thus we need to find the amount of calcium carbonate and then thus the amount of calcium carbonate in the eggshell. So once again, we're going to start at the very bottom and start with the titration. So the equation for the titration is as follows. So HCl reacts with sodium bicarbonate to give you sodium chloride, water, and carbon dioxide. We're told that 0.1 molar sodium carbonate, it takes 9.23 milliliters to neutralize the HCl, and the HCl being the unreacted HCl. So thus, the moles of sodium carbonate is N equals CV. So once again, equation, substitution, answer. And I get 0.000923 moles. However, as you can see, the molar ratio between sodium carbonate here and HCl here is 2 to 1. Thus, I need to double it. So if the moles of sodium carbonate are 0.000923 moles, the amount of unreacted HCl is double that. So it's 0.001846 moles in the 20 milliliter sample. So that's a very key component of this question. Do not forget that. In a lot of questions, they'll kind of omit this 20 milliliter sample, but we'll deal with the cards that we're given. Thus, you might remember, originally we added 100 milliliters of HCl, and then we took a 20 milliliter sample, right? If there are 0.001846 moles in the 20 milliliter sample, logic follows there will be 5 times the number of moles in the original 100 milliliter sample, because we took a fifth of the liquid, we took a fifth of the solution. So we took a fifth of the moles. So to find the original number of moles in that 100 milliliter solution, we multiply the amount in the 20 milliliter sample by 5. And that will give us 0.00923 moles. So these two are not the same number, just to make sure. And that is the amount of HCl that remained unreacted after we added the excess. Exactly 0.00923 moles. So as in question 3, we're going to work our way up. So now we're at the level of the eggshell. So I've dealt with the titration. Now I've got the speaker, I've got my eggshell that I've crushed up, I've added 100 milliliters of 0.3 molar HCl in excess. That's where we are. Recall that with these back titration problems, I need to find the amount that actually reacted with my analyte. My analyte in this case being calcium carbonate. To do that, I know the original amount of HCl that I actually added. I added 100 milliliters of 0.3 molar. And I know the amount that remained unreacted. I found that in the titration with sodium carbonate. That was 0.00923 moles that I found in the last slide. If I minus the two, I'll get the amount that actually reacted with the calcium carbonate, right? That's what we're going to do. So equation, substitution, reaction. This step here is the exact number of moles that I added in excess. I added 0.03 moles of HCl into the crushed eggshell. So that's the original amount of HCl. The amount of unreacted HCl is what I found in the previous slide using the titration, 0.00923 moles. I may be repeating myself, but it's really important that you understand what you're doing. Minusing the two, you get 0.02077 moles. That is the amount, exactly the amount of moles of HCl that reacted with calcium carbonate. Now that I've got the exact amount of HCl that reacted with the calcium carbonate, I can actually go about finding the moles of calcium carbonate that were present originally. So molar ratios. The molar ratio of HCl to calcium carbonate is 2:1. Thus, if I have 0.02077 moles, I need to half it, and I'll get exactly 0.010385 moles. And that is how much calcium, or how many moles rather, of calcium carbonate were present in that eggshell that I ground up. Then we need to find the mass. So it said by percentage mass. We're still not done yet. We're close. So we found the moles, but we're still not done yet. Still got a job to do. So the mass is the number of moles times the molecular weight. We're actually given the molecular weight. So again, equation, substitution, answer. The percentage mass is the mass that you find. So that is the calcium carbonate. So the mass of the calcium carbonate over the mass of the eggshell. And then obviously it's a percentage, so you times it by 100. And then you get 85.9%. So question 5 isn't really an example of a back titration question, it's a different question. So it's an example of a question involving a dilution. The purpose of this video was kind of to give you an introduction on the different type of questions you can get in regards to titrations. We've got some multiple choice questions for you that would be beneficial for you to do. Firstly, what I like to do in all my senior chemistry studies is to learn the type of questions I'm going to get and the different techniques that I need to learn, and then to really practice and hone in on those techniques. So knowing how to do back titration questions, knowing how to do dilution questions, knowing how to do simple titration questions, and then just spamming the questions, spamming the practice, my bad. So in question 5, we're asked, the concentration of a nitric acid in a commercial nitric acid solution can be determined by titration with sodium carbonate solution. And then the following procedure was used. So step 1, dilute 10 milliliters of the commercial nitric acid solution to 250 milliliters with water. So that's a pretty significant dilution. Step 2, pipette 20 milliliters of the dilute nitric acid solution into a conical flask. Titrate with sodium carbonate solution that has a concentration of 0.1170 molar. The equation for the reaction is shown below. In one titration, a titer, so that's the amount of sodium carbonate that was required to neutralize the nitric acid, the titer was 31.46 milliliters. We're then told to calculate the concentration of the commercial nitric acid. So that's the nitric acid before the dilution. So we're going to do that now. So as you can see, a bit of a recurring theme with all of these more complex titration questions, we tend to start at the bottom, so with the actual titration, and then work our way up to the answer. And that's exactly what we're going to do. In the question, I am given the concentration and the volume of sodium carbonate that was required exactly to neutralize the nitric acid after the dilution. Thus, using this concentration and volume, I'm going to find the exact number of moles that were required to neutralize the nitric acid after the dilution. And that's exactly what I'm going to do. So I've got my equation. I substitute. So I needed 31.46 milliliters, so that was the titer, of 0.1170 molar sodium carbonate to neutralize that nitric acid. Multiplying these two factors together, I get 0.00368082 moles. So that's how many moles I needed to neutralize that nitric acid. This is why your equation comes in really handy in regards to molar ratio. So from that equation, you can see that the molar ratio of sodium carbonate to nitric acid is 1:2. Thus, the number of moles of nitric acid is double the moles of sodium carbonate. So thus it's 0.00736,164 moles. And don't forget, it was in the 20 milliliter sample. So we diluted the acid down and we took a 20 milliliter sample and then we titrated that 20 milliliter sample. So the concentration is C equals N over V, N being the number of moles, so this value here, and V being the 20 milliliter in the 20 milliliter sample. So the concentration is 0.368082 molar after the dilution. So I need to find the concentration of the nitric acid before the dilution, and that's what we're going to do in the next slide. Again, a pretty useful equation is C1 times V1 equals C2 times V2. You may be asking, why can we use that for a dilution? And essentially, in a dilution, the volume is changing. The actual number of moles of nitric acid, in this case, is not changing. You're just dumping an excess amount of extra water to dilute the already present moles of nitric acid. Thus, N1, so the moles before the dilution equals the moles after the dilution, and thus C1 times V1 equals C2 times V2. Recall that relationship that we drew from the earlier video. So I'm gonna C1 be before the dilution. So as you can recall from the question, we took 10 milliliters, and then we took it to 250 milliliters. So that is the diluted version. So that's what we got. That was a concentration in the 20 milliliter sample, and then we multiply that by the original volume. So that was 250 milliliters. That's what we diluted it to. Rearranging for C1, you get 9.20205 molar. Also, a neat trick to know if you did it wrong is if you put the 250 on the other side, so you swap the 10 and the 250 around, you would get a number that is less than 0.368082. If you dilute something, would you get an increase in concentration? No, you would get a decrease in concentration, and that makes sense. We found that the concentration of the commercial nitric acid was 9.20205, and we diluted it down to this. If you got this and this mixed up, you would get a tiny number, and that makes no sense. That's not how dilutions work, unfortunately. So anyway, the final answer is 9.202 molar.